Okay, so today we're doing some Q&A about chapters 6 through 9 for sure. And there was at least one question about chapter 5 still, and maybe we can talk about a little bit about chapter 10 if we have time. So I went through your questions quickly this morning, and I wrote what chapter they were. So let's go ahead and start with the earliest chapter. There was, I think, a chapter 5 related question in here. Yeah, here we go. And that was, how do we determine the elements of the alternating groups? And well, to do that, you first of all have to recall what the definition of the alternating group is. AN is the group of permutations, group of even permutations on the set 1 through n. And so, you know, they're going to be permutations that you can, for example, write in cycle notation. And the main thing is you got to figure out whether a given permutation is even or not. And if you were trying to like list out all the permutations in a given alternating group, again, this is called an alternating group. You have to be able to figure out what permutations are going to be even. So like if you're thinking about a particular example, A4 in particular, well, certainly it's got to have the identity. And the identity is an even permutation. It can be written as the product of an even number of 2 cycles. Remember, that is the definition of even, is that it can be written as the product of an even number of 2 cycles. They don't have to be disjoint 2 cycles. And yeah, that can be written as a product of two cycles. For example, 1, 2, 1, 2 would be one way to write it, as a product of 2 cycles. And that's an even number of 2 cycles. So this would be an even permutation. Permutations that have, well, we're talking A4 here. There's a permutation written in disjoint cycle notation this time. That is a product of two cycles, an even number of 2 cycles. And it is an A4. It is an S4, I should say, first. And since it's an even number of 2 cycles, it's also an A4. 1, 2, 3, 4 would be 1, 1, 3, 2, 4, 1, 4, 2, 3. Those are all the ones that are the product of 2 disjoint 2 cycles that are, that are disjoint that you can write. You could switch the order of these around, but because they're disjoint cycles, they commute. And so if I wrote 3, 4, 1, 2, it would be the same permutation. But also the 3 cycles, for example, 1, 2, 3, can be written as a product of an even number of 2 cycles, though they're not disjoint 2 cycles. 1, 3, 1, 2. Right? 1 maps to 2, 2 maps to itself, 2 maps to 1, which gets mapped back to 3, and then 3 gets mapped to 1. That permutation can be written as an even number, a product of an even number of 2 cycles. They're not disjoint 2 cycles, but they are 2 cycles, an even number of them, and therefore it is an even permutation, even though it's got an odd order. It's got order 3. 1, 2, 3, 1, 2, 4, 1, 3, 4. Mind closing that door back there? Thanks. Those are some 3 cycles in A4. Are there others? Yeah, there's 2, 3, 4. And then if you, there's 4 more, which can be formed by taking these 4 that I just wrote down and reordering the numbers. Instead of 1, 2, 3, I could write 1, 3, 2. Instead of 1, 2, 4, I could write 1, 4, 2. Instead of 1, 3, 4, I could write 1, 4, 3. And instead of 2, 3, 4, I could write 2, 4, 3. And those are all distinct. And that's going to be A4. A4 does have 4 factorial divided by 2, 12 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That'll be all of them. If we're talking A5, then it would get more complicated. There would be a 5 factorial divided by 260 elements in A5. And so, yeah, that would take a lot longer. I wouldn't have you do that in an exam. But for example, 5 cycles in A5 would be even permutations. 1, 2, 3, 4, 5 is an even permutation. You can write it as 1, 5, 1, 4, 1, 3, 1, 2. That's the trick to writing that as a product of 2 cycles. They're not disjoint, but they are 2 cycles. Then there's an even number of them. 1 goes to 2. Yep. Does 2 go to 3? Yes. Well, first it goes to 1, then it goes back to 3. Does 3 go to 4? 3 stays fixed, then 3 goes to 1, then 1 goes to 4. Yep. 4 goes to 1, then goes back to 5, as it should. And 5 does go to 1. Gets mapped to 1. Okay. It's good to go over that. I think, you certainly could be asked about earlier things on the exam. Technically the chapters are 6 to 10, but you should certainly know about permutations for the exam if I had you think about an example with permutations. All right, next question. That was the main chapter 5 one. How about chapter 6? Somebody asked what needs to be included in proving 2 groups are isomorphic. I think maybe that was also related to chapter 8, a chapter 8 question, like on a homework. There was a general question, what topics, problems do you most recommend reviewing for the exam? That I said chapter 6 through 10. And how do you show an operation is well-defined, and what does well-defined really mean? Okay. Maybe well-defined I'll come back to in chapter 9, might be the best place to address that. And actually even hinting at chapter 10 perhaps. So let's look at this one first. And maybe we can look at it in the context of homework problem for today, 54, which a couple of people asked about. I think in number 54, I wasn't asking for proof, though I was asking for reasons. In general, first some general comments. In general, to show 2 groups are isomorphic, you've got to come up with an isomorphism. You got to find a function from one group to the other that's one-to-one and onto an operation preserving, and then prove all those things. Sometimes it's easy, sometimes it's hard. Okay. That said, I don't know if you've noticed, but the book doesn't always do that in their proofs that 2 things are isomorphic. They fudge a little bit sometimes, or the author fudges. For example, in the classification of groups of order 2p, this is something you should know for the exam as a fact to know. It's a classification fact. It's a part of the purpose for the course, you might say, besides just gaining skill in learning how to do proofs. Part of the purpose of studying group theory is to classify groups. Why? Because they're there. We want to understand them. They're interesting, you might say. That's what drives the pure mathematician, at least. But they do have applications too. Let G be a group of order 2p where p is prime. So this would include groups of order 6, 10, 14, right? 2 times 7. What next? 2 times 11, 22, 26, 2 times 17, 34, 38. Those would be the orders that this theorem would apply to. Then there's only 2 possible groups that G is isomorphic to. G is either cyclic of order 2p, or it's isomorphic to the dihedral group. That would be the group of symmetries of a p-gon. I shouldn't just say an arbitrary p-gon. I should say a regular p-gon where all the side lengths and angles are the same. The word regular means that. You know, a square is a regular quadrilateral, whereas a rectangle that's not a square is a non-regular quadrilateral. Same with parallelogram. It's not a square. Anyway, if you read through this proof, I think I did suggest that you do work to do it. It actually makes sense, especially if you think about the way we've talked about dihedral groups before in terms of rotations and reflections. You can make sense out of this. However, nowhere does the author come up with a function from, well, if you assume G is not cyclic, does the author come up with a function from G to dt, an actual isomorphism? The structure of the proof would hint at the way to come up with an isomorphism, but there's no isomorphism explicitly constructed in the proof. So the author is kind of fudging, okay, you might say. It's essentially the author saying the Cayley tables would be the same structure, and saying that must mean they're isomorphic without giving the full details. Probably because it would become too long that way, the proof. And the author didn't want to completely lose you in a really, really long proof or something. How would you show two groups are isomorphic? Well, we've done some examples for one thing, both practical and abstract examples. Probably on an exam, I'd sort of like say, well, these two groups are isomorphic, come up with an isomorphism. A group is certainly isomorphic to itself. And the proposed isomorphism, one proposed isomorphism would be map everything to itself. And that ends up being trivially an isomorphism. There are other isomorphisms of a group to itself in general because they would form the group of automorphisms, G. And in chapters 6, for example, they come up with examples. I mean, there's plenty of examples of isomorphisms in chapter 6, and I would encourage you to study those examples. I think I would like to talk more about the group of automorphisms maybe on Friday, but for today, we better keep going. Oh, I did want to look at number 54, sorry. Yeah, a couple people asked about number 54. On the homework for today. And I think in doing 54, besides addressing isomorphism issue, we can also address like issues about how to find the number of elements of various orders. Somebody did ask about the Euler phi function. Do you have to memorize values of the Euler phi function, for example? So we can talk about that in the context of number 54, chapter 8. So this problem here. Find a subgroup of U140 isomorphic to Z4 external direct product with Z6. Okay. Before we try to address that problem, let's think about U140 itself based on the theorems in the book, including perhaps the thing that I said to label a theorem, even though it wasn't labeled a theorem, at the bottom of page 161 here. These facts down here, essentially you could sort of think of this as a theorem, even though it's not stated as a theorem. These are fundamental facts that are worth knowing for the exam, even though it's not labeled as a theorem. Besides labeling it theorem on your own, maybe you want to box it. These are worth remembering for the exam. So U140, how do you figure out what it's isomorphic to? Well, I hope you remember from, well, either trying this problem or from the reading, the first thing that's good to do is to find the prime factorization of 140. 140 is 14 times 10. That would be 2 times 7 times 2 times 5. 2 squared times 5 times 7. Is that right? Double check that. Yeah. Okay, so that's the first thing to do to help you understand what this is going to be isomorphic to based on the theorems in chapter 8. Now, what theorem is most useful here? Well, probably that one is one thing, that corollary of theorem 8.3. Let M be the product of a bunch of numbers where those numbers are relatively prime. What would the numbers be in this case? 2 squared, 5, and 7. 4, 5, and 7 are all each relatively prime to each other. Then UM is going to be isomorphic to this external direct product. So based on that, we can say this is isomorphic to the external direct product of, I'll go ahead and write a 4. I could have kept it 2 squared. What else can we say? Now use the information at the bottom of page 161. U2 is isomorphic to 0, in other words, the trivial group. They could have written an E there instead of a 0. Actually, probably would have been better to write an E because you think of the operations in these groups as being multiplication instead of addition. But it does mean the trivial group there. It's only got one element in it, 1. U2 has one element, the number 1. 1 times 1 is 1, mod 2. U4, okay, that's what we got here, is isomorphic to Z2. It's cyclic of order 2. The operation is multiplication, mod 4 here, whereas the operation here is addition, mod 2, but they are isomorphic. They have 2 elements. Their Cayley tables have the same structure. An example of an isomorphism, if I asked you to do this on the exam, from U4 to Z2, the elements of U4 are 1 and 3. The elements of Z2 are 0 and 1. Think about it. 3 is a generator in U4. We better map it to a generator of Z2, which is 1. Yeah, that would be the only one. Map 3 to 1 and map 1 to 0. Does that make sense? U3 or U4. The elements are 1 and 3, and the operation is multiplication mod 4. Dot mod 4, all right. And Z2, the elements are 0 and 1, and the operation is addition mod 2. U4 is generated by 3, and Z2 is generated by 1. 3 under multiplication, 1 under addition. Right, 3 times 3 is 9, mod 4 is 1. Whereas 1 plus 1 is 0, mod 2. 1 plus 1 is 2, mod, which is 0, mod 2. Your isomorphism, you'd want to define to map the identity to the identity and generator to a generator. That would be your unique isomorphism from U4 to Z2. There would be no others. Though, technically speaking, you should prove it's obviously 1-to-1 and onto. You should prove it's operation preserving. For example, phi of 3 times 3 is phi of 1, which is 0. And also phi of 3 plus phi of 3 is 1 plus 1 is 0. That's one example showing its operation preserving. The operation in U4 is multiplication mod 4. The operation in Z2 is addition mod 2. So I need to check that that's the same as this, using a multiplication here and an addition there. Can you see that? Is that big enough? Sorry, I'm writing small. There's a plus sign in there. See it okay? Anyway, coming back to this problem, so U4 is isomorphic to Z2. U5, according to the bottom of the page here, is isomorphic to what? Well, 5 is prime. So to use this last thing, we want to think of p to the n as being 5 to the first power. It's isomorphic to Z sub, it's cyclic. 5 to the first minus 5 to the 0. 5 minus 1 is 4. It's isomorphic to Z4. It does have 4 elements, 1, 2, 3, 4, right? Under multiplication mod 5. For Z7, use this again with thinking of p to the n as being 7 to the first. It's going to be cyclic. 7 to the first minus 7 to the 0 is 7 minus 1 is 6. This is isomorphic to Z6. It does have 6 elements, 1, 2, 3, 4, 5, 6. It is abelian. It's got to be isomorphic to Z6. The only other possibility was D3, according to that theorem we were looking at just 10 minutes ago. Because 6 is 2 times 3, 2 times P. By the way, S3 is isomorphic to D3. But it's better to say that other theorem in terms of dihedral groups because S4 is not isomorphic to D4. It's only S3 being isomorphic to D3. The higher symmetric groups are not isomorphic to the higher dihedral groups. Okay, so that's what U140 is isomorphic to. And therefore, you can say also that the number of elements is 2 times 4 times 6, 48 elements in U140. And if you really wanted to, you could list them out. And that might have been a good thing to do for the problem because what does the problem say to do for the rest of the problem? Actually, we haven't even started the problem really. It says find a subgroup of U140 isomorphic to Z4 external direct product with Z6, which would have 24 elements instead of 48 elements. Find a subgroup isomorphic to that. Does seem pretty tricky. How would I go about doing it? I guess I would try to think about the number of elements of each order in this group, and then think about the orders of the elements in this group and try to maybe match them up in a logical way. That might be one approach. That it was a time-consuming problem for sure. Probably don't have time to finish it here in class. So you think about an arbitrary element A, B, C in this external direct product. What are the possible orders of elements? Oh, yeah, actually, we can make it simpler. Sorry. Focus just on that part there. Arbitrary element in the external direct product of Z4 with Z6 would be an ordered pair where A is from Z4, it's 0, 1, 2, or 3, and B is from Z6, it's 0, 1, 2, 3, 4, or 5. And go ahead and make a table like I do in the lectures to try to think about how many elements there are, the various orders. If the order of A and B are both 1, in other words, if A is 0 and B is 0, the LCM of 1 and 1 is 1, and there's only one element of order 1. It's the identity, it's 0, 0. That's 1 EL if you can't quite see it. 1 element. Let me just make it a 1. The order of A could be 2 and the order of B could be 1. Think about that. That would mean A would have to be the number 2 and B would have to be the number 0, right? LCM is 2 times 1 is 2. Now, let me just say 2. But there would be a unique element of order 2. Where, I should say, not a unique element of order 2 overall, but a unique element of order 2 where A has order 2 and B has order 1. The element would be the element 2, 0, in fact. Excuse me. two other ways to get an LCM of 2. There's a unique one where A has order 1 and B has order 2. It would be the ordered pair 0, 3. That's one element. Excuse me. And there would be a unique element where A has order 2 and B has order 2. It would be the element 2, 3. This has 24 elements total. What about if A has order 4 and B has order 1? Then the LCM of 4 and 1 is 4. How many elements of order 4 would there be? Well, there's 2 choices for A and 1 choice for B. What would be the choices for A? Thinking about that particular group there, what would be the choices for A? 1 and 3, the generators of Z4. Only 1 choice for B, the number 0. Overall, you have 2 elements like that. I do see I'm not being very systematic in my chart here. Let's continue with the order of A being 4, the order of B being, say, 2. The LCM of those numbers is 4. 2 choices for A, only 1 choice for B. There's 2 elements like that. Okay, let's go back to order 1 for A and say order 3 for B. Again, I'm not being very systematic in approaching these orders. Only 1 choice for A, the number 0. How many choices for B of order 3? By the way, the LCM would be 3. But how many choices would there be for B? How many elements in Z6 have order 3? And what are they? Certainly 2 does, right? 2 plus 2 plus 2, mod 6 is 0. Anything else? 4 has order 3. So there's 2 choices for B, 2 choices overall. I think I better stop for sake of time, but you could keep going. You could try to find, this would be too long for an exam problem. You could try to find the number of elements of the various orders here in Z4, external direct product with Z6. The total number of elements should add to 24. This is just one way to solve the problem. Maybe there are others. Again, this was a long problem. And then think about U140. It probably would have been good to list out the elements. And try to identify a way to make a subgroup that's got the same structure, essentially. That was a tough problem. May still not be clear how to do it. You may want to think about the subgroups that would be cyclic and maybe non-cyclic as well. It was a tough problem. Your final answer should not be a cyclic subgroup, because it's got to be isomorphic to this, which is not cyclic. Maybe this was not the best approach because it takes so long. Maybe a better approach would have been looking at U140 and first looking for an element of order 4 and then also an element of order 6. You know, you've got to have those kinds of elements in there if it's going to be isomorphic to this. And think about the subgroup that the element of order 4 generates and the subgroup the element of order 6 generates. And perhaps, if you did this, this would have probably been good intuition. Perhaps try to find all products of the elements of order 4 and the elements of order 6 that you're thinking about. That might have been a quicker way to go. Maybe we should spend a little more time on this. Could Mathematica help us? I think so. Though you didn't have to do this. It's time consuming no matter what way you do it. But I mean, I think this ultimately might have been a little quicker. Let's see here. Coprime Q, I think I showed this to you before, way back the first week or two, can tell you whether two numbers are relatively prime or not. If I do this, I'll get a bunch of trues and falses corresponding to whether I is relatively prime to 140 or not. First one's true, in other words, 1 and 140 are relatively prime. Second one's false, 2 and 140 are not relatively prime. Third one's true, 3 and 140 are relatively prime. We can make ordered pairs to see the numbers themselves. Could also put this in tabular form. So I can quickly see the elements of U140 here. 1, 3, 9, 11, 13, 17, 19, certainly all the primes that are not 2, 5, or 7 are in there. But there's some non-primes that are not multiples of 4, well, ultimately 4 or 5 or 7. For example, 33 should be in there, 11 times 3. Yep. And then you could try to go through and figure out the orders of these things quickly, probably. You could make another table where you square them all for perhaps here and mod by 140 to see the elements of order 2. Could go comma mod I squared comma 140. I won't bother getting rid of the ones that are false, but for the ones that are true, which of these gives you 1? Or maybe I should go out of the 4th so I can look for elements of order 4. 13 has order 4, it looks like. There's a 1. 27, well, okay, they could have order 2. So these are not ruling out the elements of order 2, because if the element has order 2, when you raise it to the 4th power, it'll still equal 1. So I'd have to first figure out the elements of order 2, then order 4, then order 6 I could look for as well. Ruling out first the elements of order 3 as well. So I'm sure nobody did that, because you probably wouldn't have thought to do this. But this would be some Mathematica code that would help you do calculations faster. I will share this with you. Coprime Q tells you whether two numbers are relatively prime or not. And mod, of course, does modular arithmetic. Let's continue dwelling on this a little bit, because there were some other questions related to external direct products. How do you find a generator of an external direct product that happens to be a cyclic group? Probably some experimentation. If we consider maybe a simpler example than Z4, though that's not cyclic, right? Because 4 and 6 are not relatively prime. There's a theorem in chapter 8 that says an external direct product like this is going to be, of cyclic groups is going to be cyclic itself if and only if the orders of these groups are relatively prime. 4 and 6 are not relatively prime. So this is not a cyclic group. But how about like the external direct product of Z2 and Z3? 2 and 3 are relatively prime. This should be a cyclic group. It should be isomorphic to Z6. How do you find a generator? Either a little bit of thought and or experimentation is my best recommendation. And it's small enough that that's not too hard. You can even quickly list out the elements. The ordered pair 0, 0, then 1, 0, then 0, 1, then 1, 1, then 0, 2, and 1, 2 are your 6 elements in this external direct product here. These are not the same groups, right? Z2 external direct product with Z3 is not the same group as Z6. The elements are not the same, and the operations are not the same, but they are isomorphic. They have the same Cayley table structure if you made the Cayley tables, and the same number of elements of each order, and so forth. We're looking for a generator of this. So we're looking for an element of order 6. I guess you could think about, what would make the LCM of the order of A and the order of B be 6. You could be a little bit more systematic. That will happen if the order of A is 2 and the order of B is 3. So A has got to be the number 1, and B either has to be the number 1 or the number 2. There's your generators right there. Right? And you can double check it. 1 plus 1, 1 plus 1, 1 is 0, 2. 1, 1 plus 0, 2 is 1, 0, right? First component is addition mod 2, second is addition mod 3. Double check those. I could make a mistake. 1, 1 plus 1, 0 is 0, 1. I'm really adding one to itself each time here. I'm just bringing these things down. 1, 1 plus 0, 1, bringing this down, is 1, 2. And then 1, 1 plus this one, 1, 2, is indeed 0, 0, the identity. We add 1, 1 to itself. 1, 2, oh, well, okay. Multiplying it by 2 here, essentially. Multiplying it by 3 to get this, then 4, then 5, then 6. When I say multiply, I mean, because the group operation is addition, when I write this, it really means 1, 1 added to itself 6 times. And that does equal 0, 0. If it was a bigger group, it might be harder, but probably the same approach. Maybe thinking systematically about the LCM would be a good way to do it instead of just guessing and checking. Yeah, that probably is a better way to start. Somebody else asked about whether external direct products were abelian, I believe. And the answer is it depends. Yeah, are external direct products commutative? The answer to that is it depends. Certainly the external direct product of 2 abelian groups is abelian, or the external direct product of n abelian groups is itself abelian, because there would be abelian component-wise. If G1 and G2 are abelian, let's just do it in the case of 2 groups. That does imply that the external direct product of G1 and G2 is also abelian. No conditions on the order. This was not true, right? If I get rid of if I change the word abelian to cyclic, to the cyclic theorem, you have to add the extra condition that the 2 finite groups you're talking about have relatively prime orders. Here in this statement, I'm not even saying these are finite groups. They could be finite or infinite. The idea of the proof, Well, it would be, take the product of an arbitrary element here. Say AB times CD. It's an abstract one, so I'm going to use multiplication. That'll be component-wise multiplication here, ACBD, and then use the fact that G1 and G2 themselves are abelian to write that ordered pair, and then separate that out by definition of ordered pair multiplication in this external direct product. So that's the idea, and it's fairly simple. I don't know if you meant this, the person who asked this, but you might also wonder, is this O plus operation for external direct product, is that an abelian operation? In other words, is the external direct product of G1 with G2 the same as the external direct product of G2 with G1? Can I switch around the G's, the groups themselves? Well, they're not equal as sets, so you can't literally say this equals this, but they are isomorphic. I'm writing it as a question, but it's actually true. They are isomorphic. The answer is yes. Well, this also addresses the question of how to come up with an isomorphism. Got a guess? What should phi be here? What should its formula be that is most likely to be an isomorphism? What is a natural formula? Emphasis on the word natural, like we talked about on Monday. What's a natural formula to use for phi? Say if I say the input here is, well, let me use lowercase g's. What's a natural thing to guess might be an isomorphism? Yep, switch them around, G2 comma G1. Show it's one-to-one onto an operation preserving. Is it really operation preserving? Okay, let's go ahead and check it. There's phi applied to an arbitrary product in the domain group. How do you figure out what this is? You got to, well, first figure out what that product is, but again, it's done component-wise. Oops. It's easy to get confused here with your symbols. Then use the formula for phi. That equals, so switch around the components, the order. And does that equal this? Well, go ahead and compute this. Got my commas. First one, the G1 and the G2 get switched around. Second one, the G1 prime and the G2 prime get switched around. But then by definition of multiplication in the external direct product, this is the same as that. And that is the same as this. Match. We are happy. Right, to the uninitiated person off the street, this just looks like a bunch of nonsense, right? What in the world are you doing? But to a mathematician, you are proving something that's definitely true, and it's a natural kind of thing to do. Guess I skipped over chapter 7 with our chapter 7 questions here. There was, can we spend more time on the orbit stabilizer theorem and its proof? I think for the sake of time, I'm going to skip that one because there were a lot of questions about chapter 9. Let's spend our last 15 minutes looking at chapter 9. Here's again the definition of a normal subgroup. A subgroup H of a group G is called a normal subgroup of G if each left coset equals the corresponding right coset. Or probably a better way to say that is the left coset of H and G containing A is the same as the right coset of H and G containing A. Is the best way to say that. And we denote it by this. You put a little extra line on your subgroup symbol, make it a triangle. That is standard notation for H being a normal subgroup of G. Somebody did ask, I believe, are normal subgroups commutative? Are they abelian because AH equals HA? Is that saying something's abelian? I forgot how the question was phrased. In the definition of a normal subgroup, if a subgroup is normal, does that mean it's abelian? The answer is no. Even though AH equals HA. The book emphasizes that these are equal as sets are and ha equal. Take on me. You know that song? Take on me. It's by a group called Aha. That's a joke thing. So are and ha equal? Well, not in general. But if H is normal, they are equal. As sets, that does not mean A times little h equals H times little a for all little h and h. It does not mean that. It means given an arbitrary element of AH, say write it A times little h, if little a times h equals capital H times a, ha, then there exists an element of H, possibly different from the little h here, call it H prime, such that A times little h equals H prime times A. Why? Because, again, we're assuming AH is in, A little h is in A capital H, this left coset. This element is in this left coset. But if these are equal, that means it's in this right coset as well. But by what that right coset is the set of all products like that. So there's some H in capital H, making A times little h equal to that element of capital H times A, but not necessarily the same element. Could be a different element, call it H prime. By the way, in case you're wondering, the primes here have nothing to do with derivatives. H prime could be the same as H. And in fact, that would be true if H is abelian. Or I guess I should say G is abelian. If G is abelian, every subgroup is normal. If G is abelian, every subgroup of G is normal in G. But there are non-abelian groups that have normal subgroups as well. In the case where G is abelian, you could use H prime equals H itself. But in general, you can't, because in general, you can't assume G is abelian when you're doing theory about normal subgroups. What's an example of a non-abelian group that's got normal subgroups? Non-trivial normal subgroups, I might say. The identity by itself is always a normal subgroup, and the entire group itself is always a normal subgroup. but those are trivial, right? Is there a non-trivial that's got an order between 1 and the entire group order? Well, one prominent example is that for any n, an, the symmetric group is always a normal subgroup of Sn. The alternating group on n objects is always a normal subgroup of the symmetric group on n objects. The group of even permutations on n objects is always a normal subgroup of the group of all permutations on n objects. And in fact, this fact is a special case of a more general fact. If the order of G is, say, n, and H is a subgroup of G with order equal to n divided by 2, implicitly assuming there that that's an integer. So I'm implicitly assuming n is even here. Then H is a normal subgroup of G, whether G is abelian or not. So if your subgroup has half the size of the entire group, it's automatically normal. That is mentioned in chapter 9 somewhere, I'm forgetting where. Emphasized, something like that. What about the normal subgroup test? Subgroup H is normal in the group if and only if this set is a subset of that set for all x and g. So to use this, you got to pick an arbitrary x and g and show that that's a subset of that. Show that every element in here is in there. That's easy for abelian groups, but it then can be harder for non-abelian groups. One good example to think about is actually to think about groups of matrices, the GL groups, and a certain subgroup called the SL. I don't know what she's referring to there, what family. Okay. GL2R, GL stands for general linear group. 2 by 2 matrices with real number entries and a non-zero determinant. The operation is matrix multiplication in this case, not matrix addition. Matrices, groups of matrices can be under addition, and when it's under addition, you don't need the determinant to be non-zero. But when the operation is multiplication, which is a more interesting operation, then you need the determinant to be non-zero to be in here. Because if the determinant is 0, then the matrix is not invertible. So that's why we assume the determinant is non-zero. SL stands for special linear group. 2R means set of all 2 by 2 matrices with real entries whose determinant equals 1 exactly. That's what the special linear group is. These are infinite groups. However, in spite of that, SL2R is a normal subgroup of GL2R, and they verify that essentially with the normal subgroup test. Give me an arbitrary element of that set, show it's also in that set, because that's what it means to show this is a subset of that. So give me an arbitrary element X in the entire group and an element in the subgroup. I need to show that product is also in the subgroup H, which is the SL right there. How? Well, you have to ask, what does it mean to be in the special linear group? It means the determinant is 1. That's what it means. So we got to take the determinant of this matrix. This is a matrix here, even though it doesn't look like a matrix. By properties of determinants that I did have you use on one assignment back in the first week or two of class, the determinant of a product is the product of the determinants, and with inverses, you can bring the inverse out as a -1 power. That's a property of determinants, that these are equal. The book's not proving that, it's assuming you've seen that in linear algebra. But hey, H is in SL, so its determinant is 1. You can replace determinant of H with 1, it goes away. And these are two numbers whose product is 1. They're non-zero numbers. This multiplicative inverse of this non-zero number does exist. You're not dividing by 0 here. This is the product of two numbers, neither of which is 0. And they are inverses of each other, multiplicative inverses. Like just this is like 5 times 1/5 equals 1, for example. So that verifies the determinant of this is 1, and that's what it means to be in SL, and therefore it is in SL. And therefore this is a normal subgroup of that by the normal subgroup test. It's got a somewhat similar feel as just, well, I guess the main thing is just showing one thing as a subset of the other or not. It's worth studying example 9 well as well to see that this is a normal subgroup of A4, whereas this is not. This is a good example to see. And by the way, if you didn't notice, the back of the book does have Cayley tables, including a Cayley table for A4. Good to keep that in mind if you haven't noticed that. It can help you check examples. Running very low on time here. Let's spend our last 4 minutes talking about factor groups and their applications. And the well-defined issue comes up here, and I'll try to address that briefly as well. So again, a factor group, given a group G and a normal subgroup of G, so this is one reason normal subgroups are important, is they help you define factor groups. You can define this set even when H is non-normal, but it's not a group, it turns out. It's only a group when H is normal in G. G by H, the factor group of G by H, is that G divided by H? Is that what that is? Well, kinda, but it's not a literal division. But it's kind of like a division in some ways, and so that's why they use the symbol. It's, what is this? This is a set of all left cosets of H and G. The elements of the factor group are cosets. The entire coset is an element. Each entire coset is an element of the factor group. Under what? What's the operation? Under this operation. To multiply these two left cosets, the left coset of H and G containing A times the left coset of H and G containing B, multiply the representatives. To get this new coset, the left coset of H and G containing A times B. That's the operation. And that's how you do computations in factor groups. Multiply the representatives. Question?
Is there a reason it's just the left coset?
Just because you have to pick one, you can do it with right cosets as well. Thanks for asking. But you do have to show this operation is well defined. Somebody asked about that. What does well defined really mean? It means it makes sense, is in a nutshell. But why do you have to prove it makes sense? Doesn't this obviously make sense? No, it doesn't obviously make sense, because there's an issue with the fact that cosets can have different representatives and still be the same coset. Does this formula still give you the same answer? That's the issue. Got to show the correspondence is well defined. It's actually a function. If you got AH equaling A prime H, so A and A prime are possibly different representatives of this left coset, and B H equaling B prime H, so B and B prime are possibly different representatives of this same coset. Here's your goal, does this still be true? Are these two left cosets the same? If I use the formula with A and B, get an answer. Do I get the same answer with A prime and B prime? Are those two sets equal? And that's what they verify using properties of cosets, but it's tricky. But very important. Make sure you understand this proof. Why are they important? 1 minute. Hey, applications of factor groups. One application is called the GZ theorem, which is a pretty weird theorem, actually, when you really think about it for a while. If G is a group and Z of G is the center of G, then you can say that if that factor group is cyclic, then G must be abelian. Which is weird because that would also mean the center of G is the entire group G, when G is abelian. And it would also therefore imply that the factor group must be trivial. If I'm doing the factor group of G by G itself, if Z of G equals G, then that's got to be just a one element group. It's just one coset by itself. So it's kind of a weird theorem, but still important. The book emphasizes that you actually typically use this the other way. If G is a non-abelian, then the factor group cannot be cyclic, and that might be helpful in some situations to know that. Non-abelian groups cannot have cyclic factor groups of when it's G modded by Z of G, I should say. That particular factor group cannot be cyclic. Other ones could be. This factor group is also isomorphic to the group of inner automorphisms. I haven't focused on inner automorphisms in class here with you guys. Sorry, going a little bit over time. I think I will try to on Friday. Let me just end in 10 seconds to say that this paragraph emphasizes the importance of factor groups. You can prove things about the original group ultimately by using induction often when you use factor groups. This is one example, Cauchy's theorem for abelian groups. Somebody asked, does Cauchy's theorem related to Cauchy sequences? The answer is no. Cauchy did lots of things. All right. See you on Friday.